Recording in progress. If you don't want to be recorded, leave the room now. Share content. Screen. Start broadcast. Okay. Yes. Haha, haha, haha. We are here. AJ, guess what I found?
What's that?
Print out.
No. Right. One more.
Pass it around. No, we don't need to do all that. Okay, so first off, welcome to Quantum Information Science here at Dartmouth College. This is Physics 116. You can take notes, but let me tell you, the notes are already typed. Haha, haha. What we will be doing in this course is a graduate level introduction to quantum information science. The entire idea of this graduate introduction, oh, you printed it out for everyone. Wow. Well, that was surprising. Great. Anyways, you guys can read this and you will find out that this course has been planned out and thought through. Rather than reading the syllabus, we'll just go through it as a first lecture. Okay, so the first thing that we're going to discuss is where this class will be held. Right now, the class is being held here in Wilder, of course, obviously. Oh, shoot. Give me a second, guys. Forgot. We have to wear masks?
No.
Great. I've been traveling a lot too, but I've also caught COVID twice, so you guys are worse off than I am. All right, sorry, I took some notes for a minute. All right, so first off, where you guys are here, you found the classroom, good job. If you're watching this anywhere, then you must have found the video. Right, so where? Virtually. And in person. We're in Wilder Laboratory. It's important that I say that we're in Wilder Laboratory because I want you all to know that you are in my department. My department, I appreciate people being respectful of one another, people being inclusive of others' identities, being respectful about scientific discussions, and cognizant of the fact that we're here to do science. Okay, so first rules of the classroom. You can ask as many questions as you want. Feel free. I will stop you if I feel tired of you asking me questions, but that is not because I don't want you asking questions. It might be because we're derailing the plan for the lecture. We'll have office hours every single day from 5 to 6. So if you have too many questions, just come to office hours. We can talk for a whole hour. But it's also every day, so don't set up another time. Just come 5 to 6. You don't need to schedule anything. If you need to schedule something, schedule it, but just 5 to 6. We'll just keep it that way. The office hours will also be held virtually and in person. I will be posting the Dart Go link that will hopefully work. So then you'll be able to get to the office hours virtually if you want to go that way, or come to class virtually if you'd like to go that way as well. Okay, so that's the first thing for where. So that's where you are right now. Where we are as a collective society is 2022. We're ending a pandemic. I'm allowed to take my mask off. Quantum computing is taken off instead of meteoric way. There's a lot of different companies and a lot of investment from a lot of different people, including our own department with new hires and the present offerings that we have. So who's teaching this course? I am Professor James Daniel Whitfield. You can find out more at my website, jdwhitfield.com. I've been working on quantum computing since 2006 when I opened my first copy of Nielsen and Chuang. The book is extremely dated, but that's also because I'm dated, so it's all good. We're not going to teach out of Nielsen and Chuang because the book is the same book I had when I started grad school. I was in the same student as you guys were. So we're going to use that book as a foundation to go further and to learn more. So I'm James Whitfield. I have 20 years of experience. Well, this doesn't add up. Less than 20 years of experience. Greater than 10 years of experience. I've been at Dartmouth since 2016. Taught this course twice before, in 2018 and 2020, as you have some alumni of the 2020 edition here. This edition will be, I think, the best so far because I really care this time. I also have a TA who's fantastic. Let me introduce AJ. AJ Cressman. I don't know if he wants to do it himself, but nonetheless, I will introduce our TA. Our TA, AJ Cressman, is from the same county that I'm from. In fact, went to the same high school I went to. We're in the same science and tech program. Okay, not the same time, but the same place. So it's nice that somehow he ended up here at Dartmouth College. It was funny because reading my thesis and he noticed inside the acknowledgements that I shouted out PG County and he came to talk to me on winter break. And then I realized people were reading my thesis. I mean, it's always fun when it does. If you read my thesis, you'll find large portions of it copy and pasted into the notes for this course. The notes for this course are intended to be a refreshing update to way that people have taught quantum information science. If you read Nielsen and Chuang, or if you haven't, either way, you go open Nielsen and Chuang, look at the layout of the textbook, and you go open up Quiz-Kit textbook, go open up Press Skills notes, go open up many different sets of quantum information lectures. They'll all be structured very similarly. Our course will be structured somewhat similarly because it's the same information, but we're going to try and take a somewhat novel approach to how we approach these things. AJ has experience as a professional programmer, experience as a high school teacher, and he is a graduate student, third year, second year, fourth year. And he's working with Rahul. I have no idea how to source this.
Sarpeshkar, SARPESHKAR.
Right. So that's AJ. I myself have a research group, Brent, hi. I have a research group with a lot of people, a lot of funding, and we do quantum information science quite broadly with the focus on quantum simulation for quantum chemistry, many other things included. So then what? What is the plan? What is the plan? How are we going to actually accomplish this course? And so the way that this course is laid out is structured in a way that makes sense to me, and I'm trying to impart the idea to you so that you also understand what you're going to be doing. Of course, it's not going to be an easy course by any conception of the word easy, but that's not what it's intended to be. If it were easy, you wouldn't learn anything, right? That's the easiest course I took in college. It's complicated, but I didn't learn anything because I breezed through it and I don't remember anything that happened. So I don't want you to breeze through what's going on here. I want you to take the time, appreciate it. Part of my teaching philosophy, which we'll talk about in a little bit, is aesthetic appreciation. It's getting you to appreciate the concepts that we're talking about and understand how they connect to things that you're interested in. We'll talk about things that you're interested in a moment. But first, what is the plan? So what is quantum information science? We'll talk a bit more about that. And the way that this is going to work is that we're going to have units, and our units will be structured as follows. So we have a unit, and each unit will be 3 weeks. We're going to use every X hour. You're not required to come to every X hour. You'll come required to come to the second and third X hours, and you're not required to stay either. Just come check in, say hi, show me whatever you got. The X hour is not exactly optional, but it's also not structured. So you can take that how you want. This is a learning environment, so we want to make this the best learning environment. And it's not a good learning environment if you're not there to learn. So come learn with me. This is what we're going to do. So one, we have 2, 3, 4, 5, 6, 7, 8, 9, X, X, X. Now, each unit will be of the same exact structure, which is the idea. We want to have some structure and scaffolding that we don't fall apart. What we're going to do today is discuss project assignment goes out. You get the project assignment by the end of the lecture. Tomorrow, we're going to have X hour. X hour is 1:20 to 2:10. The X hour will be held. And again, it will be open format, but the X hour tomorrow will be about helping you get a computer set up. We're going to use heavily Amazon Braket for the coding aspects of this course. So we'll be coding aspects of the course. And we'll also use the X hour tomorrow to talk about any potential ideas that you have for projects or potential ideas you're already working on that are connected to quantum information science that would make a small 3-week chunk that you can do, 9-week chunk you can do over the course of this term. The second X hour will be the lab part 1. The third X hour will be lab part 2. Okay, the project goes out. We have lectures. You are going to turn in, and this is actually where I came into conflict with. You're going to turn in your first assignment on Friday. Okay, you need to give me 300 words about a project in quantum information science, preferably connected to something you're actually interested in. If you are thinking about doing a PhD project and you don't have one, come talk to me. We can discuss ideas that might make a good 9-week seed to something that would grow bigger. If you already have a PhD project in progress, bring that and just use that, right? If it's connected to quantum information science, even vaguely, then we're going to connect it further and you'll expand on it over the course of 9 weeks, learn about other aspects of quantum information, bring it to your project. That's the idea of the course, is to send you to your PhD project, not take you away from it. So come with whatever's interesting to you, and that you should turn in the first hand-in. So the project hand-in will be on Friday.
I'll say that tomorrow, setting up your computer will not take very much time. If you have no idea what you want to work on, that's a really good time to come and talk and work something out.
Yeah, that's the primary use of tomorrow, is to talk about your projects and set up your computer if you have no idea what you're doing. If you do, then great. Still come, just come, you can hang out, just read a book, who cares, right? We're gonna sit in this room and I think here, I don't know if someone else is using the room, but we'll use this room preferably. We have enough space if people spread out. And then if you have a question about coding or whatever, just walk around, ask somebody, ask me, ask whoever, you can ask your colleague. If you're a great coder, help out the person who's not a great coder, somebody's never used Python, show them where Python docs are. If you know what you're doing, then help out, right? It's not the idea is to hoggle the information. There's a saying I heard not too long ago, someone said, give away your Legos. Right? This is Wilder. We started off with the point that this should be an environment that's collegial. That means that if you give away your Legos, you shouldn't steal all your Legos and then go build the building and not tell you about it, right? So don't plagiarize or otherwise scoop each other, right? Work with each other. That's the idea. So give away your Legos so you can have more people play with you. You can build bigger things. So that's one thing. All right, next thing that we have here, the referees. So the projects that you have are going to be divided. And the importance of the project is not so much you give a 300-word abstract that turns out into a fantastic project and you get a Nobel Prize at the end of 9 weeks. No. The goal is you learn a lot about how to be professional. This is one of the aspects of the class is about professionalism. This class will prepare you both for academic or industrial research. So there's a huge emphasis on being professional, on being technically accurate, and on creativity. So these are actual 3 criteria. In order, it would be being technically accurate, then being professional, and then being creative. So these are how we will judge your assignments. Okay, we're not going to judge you on completeness per se. If you're not a programmer, I don't expect you to become one in the scope of 9 weeks or in the scope of 2 weeks, as is the case for the lab. But I do expect you to try and demonstrate what you've learned. The homework, the same thing. I'll try and have the homework done either tomorrow or Wednesday. And the homeworks will be for the entire unit. And it will include several different components. And in those components, you will be able to select some of the problems. And you will type up the problems that you've selected. And you can do all the problems, but you don't need to turn them all in. And in fact, I really want you to turn them in to illustrate you know how to use tech. You have the time to actually type up some answers and show that your responses are been well thought through. And if you have questions about them, of course, talk to your colleagues.
In addition to the project
Yes.
assignment?
You will have homeworks. There will be no tests because last time the class got overwhelmed, so we took out the tests. So it'll be the labs. There will be a homework for each unit. The homework in the labs for each unit will count for a total of 20 points, 10 each, and that's per unit. So that adds up to 60 points over all the homeworks and all the labs. And it's really not even based on completion. It's based on attempt, creativity, professionalism, and just doing your best. Then the project assignment will count for the other 40 points of your grade because there's a lot of aspects of the project assignment. I'm asking you to give me an abstract by the end of the week. So I was told this is too much, but you guys all seem like adults. If anybody feels like they can't do it by next week, there's a backup date. Backup. So let me just do this differently. So you shouldn't think of it as a backup. You should turn it in on time because what's going to happen on Monday, what we want to do is actually assign referees. So you will all be responsible for refereeing each other. This is journal 116, right? So last time, I don't know if you collected the names of everyone else, but try to see if you can just find their names, emails on the department webpage. What we're going to do is actually give you the illustration of what happened at the end of last term. Everybody, pulled their teeth out, cut their feet, and just bled out a lot of blood. But at the end, we got back all these really nice projects that were done, completed. We had presentations and a nice little workshop for everyone to present, everyone and giving referee feedback to each other. You're going to submit the abstract. You submitting your abstract is not so important that your abstract's completed, done, or whatever, but it should be clear about what it is. And once that abstract's submitted, we're going to give it out to other people to referee it. Not that they're going to referee it in any terrible way. Again, respect, collegiality is one of the underlying principles that we started this conversation with. And so what we're going to do with the referee reports is follow APS referee reporting guidelines. And we'll ask you to submit a few paragraphs that address whatever deficiencies or strengths of that abstract are. And so you'll have a week to do that. So this is reports due. Okay, and then the final project check-in. And the homework's due. Okay, this is the unit. It's gonna rinse, wash, repeat. 3 times, 3 weeks, we're done. June 1st, okay? Guys, ready for this? Guys excited? Good. Okay, so that's what? I just said units, but we didn't say what the units are. So let me give you a sense of how we are going to impart the broad aspect and ideas of quantum information science to you as neophytes or otherwise already professional quantum information scientists. Whatever might be the case, I want you to get something out of this lecture series. So we're going to structure the lecture series in a way that's at least interesting, even if you've already seen everything. So if you've read Nielsen and Chuang from beginning to end, this course will still be interesting to take. I hope. So how? We have 3 units. The first unit is on kinematics. I taught freshman physics several times, and none of them successfully. Well, they're semi-successful, but none of them as successful as I would have liked. There's a lot of bells and whistles, and you need to be really fancy about it. But the problem with kinematics in freshman physics is that there's nothing interesting about kinematics in freshman physics. Newton did this many hundreds of years ago, that now we're just updating a bunch of things that he did, talking about differential equations at the lowest possible level. And you guys are all mathematically sophisticated, but we're going to take the same ideas. And the thing that I like the most about teaching physics 13 is thinking about how to teach introductory physics. I'm teaching this like it's an introductory course because one of the ideas that we had of this graduate course, Quantum Information Science 116, is that it's not distinct materially from the undergraduate version. It's the same information, just at a deeper level. And to get to a deeper level, we're going to structure it in a way that gives you a deeper insight to this information. So we're going to start off with kinematics of quantum mechanics. Quantum kinematics, however you want to think about this, what we're going to do is start with probability first. With the concept starting with probability first is going to allow us to understand quantum mechanics as an extension of probability. If we do it this way, we get back a lot of physics, a lot of mathematics, without going too far away from the main line, right? You need to draft other things onto the main line, and we'll try and give exercises to illustrate how things come onto that main line of kinematics. But we're going to focus on the kinematics in the lecture series. In the lab, we'll be looking at things that illustrate how these kinematics come to light, how they connect to devices, and how they connect to measurement, how they connect to understanding a bit, how they connect to understanding a qubit. So we're going to do all these over the course of the lab experience. You get as far as you can in the 2 weeks of lab. Unit 2 is foundations of quantum information science, of quantum information processing. So there's a conference every year that's held. It's called Quantum Information Processing, QIP. It's a fantastic conference. The idea of this course is you should be well prepared to go to that conference and understand at least what the major themes are. And so we're going to do it at the major theme level. We're not getting the details of the specifics of any one of those papers that will be at any one of the tracks in QIP, but we'd like to get you up to a level that you understand why there is a conference for QIP at all. What is quantum information processing? To that end, what we're going to focus on is things that are not quantum information processing. So we're going to focus on it in a complementary way. So we're going to think about what can you do without a quantum device. This is matrix product states. We'll talk about entanglement theory. What can you do without a quantum device? You can do certain classes of gates that are not universal. You need to add more gates to make it universal. And that's exactly where we get to a lot of concepts about stabilizers and quantum error correction. Quantum error correction itself is very important for even maintaining the idea that quantum devices can be used as computational artifacts. The fact that it can do computation at all requires that you're able to control information. Controlling that information requires quantum error correction, quantum control, a lot of these ideas. We won't talk about quantum control very much, but if this were Lorenza Viola, who originally taught this class in 2005, if it were her class, there would be a whole section on quantum control. If you're interested in quantum control, do not let it being not included in the lecture series deter you. You may choose quantum control for your project if that's what's of interest to you. 3, the quantum algorithms. There's also a very famous webpage started by Stephen Jordan called the Quantum Algorithm Zoo, and you can feel free to go peruse the Quantum Algorithm Zoo, but it's a zoo. It's actually very complicated to read without an actual background in computer science. 1 second. Handwriting bad?
I was asking what the name was.
Quantum Algorithm Zoo.
No, I mean,
If you Google it, you'll
forgot
find
the
it.
name of the guy.
Stephen Jordan. Stephen Jordan does actually a lot of really nice work. If you want to look for some small projects, he has a couple papers going back to early 2000s, around 2006, 7. Quantum gradient algorithms, kind of cool. This one, if you want to look at something. Anyways, quantum algorithms do. We're not going to be able to go through we're not going to be able to go through and do actual zoology of all the different algorithms. We're not going to go through all the details of all of them. So what we're going to do instead is take one algorithm and go very deeply to the bottom and actually see how it comes back up and gives you all the rest. Okay? What we're going to do is start with Grover search. I don't know how many people have heard of Grover search or have actually been through the details. Okay, well, that's fine. We'll go through it in high detail, maybe not high detail, but in whatever detail you already learned it. This will be a review from those of you who've seen it before, but we'll take out some very important aspects of that review, which are the fact that it's a product of reflections. This product reflections idea gets extended vastly into many directions, and we're going to follow those many directions that it gets extended into. We'll end up in the quantum singular value transform, which captures a lot of other quantum algorithms. We'll talk about how VQE and how Shor's factoring algorithm are disconnected and how they are connected, what the difference is between them, and get some sense of how we can even make arguments based on computational complexity and build off of the foundations of quantum information processing. So that's our 3 units for the course. There'll be lecture notes posted for all these things. I can give you other people's lecture notes. I can give you other people's references. I can give you things all day. But there's so many things that it's not the point to give you more things. In fact, you can read review articles going back to the 90s, but you just be reading review articles going back to the 90s, you wouldn't make it to 2000 by the time you got to the end of 9 weeks, right? Just, nature of things. Okay, so that's how, for the project check-ins, there's a number of different ideas that I can provide you for projects, but I think the best thing for you to do is for you to come with whatever idea, whatever it was that inspired you to take this course, and then we can discuss it. Think about how to narrow it down to 9 weeks, how it connects to the broader picture, how it connects to other ideas that are in the literature, how some inkling of an idea you have can be fleshed out and look at the other literature that's connected to it. It's very hard for me to give you a full literature review for any particular topic, but there's many different topics that are interesting. We're going to be using Amazon Bracket. You will each have 500 credits, so that's actually quite a bit. For about $1 of credit, you can run a single quantum experiment. So you run a circuit and you do 1,000 shots on a superconducting device, and it'll cost you about $1. On the ion trapped quantum computers, You can run about 100 shots and it'll cost you about $1, but it's more precise. So then you kind of get a trade-off there. In fact, even looking at the trade-off between how far $1 would get you would be a fantastic project, right? If that's something you were interested in, thinking about how quantum computing intersects with actual cost for a computation, you can actually think about what can you do for $1? Which device is the best dollar for dollar device, right? I mean, there's easy ways you can think of small projects that would work really well over the course of a 9-week scan, given that you have these resources available to you. Yeah, these are just a list of ideas of things that I think are cool. Some of the things that we'll cover in class is we will talk about random circuit sampling. This will be the highlight of Unit 1. Random circuit sampling is quite an interesting problem. It actually shows up very nicely for the context that we will uncover quantum information theory, in that we start with kinematics. We think about what this gives us. We're going to start with probability. We start with the kinematics of probability functions to think about how probability functions can evolve without even worrying about anything about actual random events. I mean, we worry about random events at the very beginning, but then there's kinematics after that. Just how can this thing be allowed to transform? Well, the same thing for the quantum situation, but in going through the quantum situation, this will lead us directly to thinking about how do we compare two different probability distributions? How do we compare two different quantum states? How do we compare two different benchmarks to our quantum device? And we'll look at deficiencies of the benchmarks that people have been using, the linear cross entropy benchmark. We'll talk about entropy. We'll talk about why it's a cross entropy. We'll talk about what the linear cross entropy is. We'll talk about why this benchmark is not a great benchmark. We'll talk about what are some ideas that you could use instead. And we'll try and get you a full appreciation by the end of Unit 1. That's the goal. Instantaneous quantum computing, I don't know enough about it to say anything, but I think it would be a cool project. Sine cosine decompositions, Gibbons rotations, linear combination unitaries. These are all things about compiling gates. You can imagine doing quantum control, that you can imagine you're interested in how superconducting devices work, and you just spent the entire time trying to control Rigetti's device from the cloud. That would be a completely valid project to think about how do I actually implement a rotation from one particular quantum state to another optimally. This is an entire field in and of itself. Any of you who have worked with Professor Ramanathan will know that in NMR, a lot of these techniques and ideas were developed in order to do optimal control. Professor Viola also did bang-bang controls, thinking about decoherence. We'll talk about decoherence inside of Unit 1, because that's also part of quantum kinematics. We'll talk about how density matrices can change, what sort of things we'd expect to happen. We'll talk about how do we even understand what T1 and T2 times are from a kinematic point of view. Right? These are often ways people use to characterize how good the quantum device is. We want to understand how those characterizations are showing up and how we can understand other characterizations, even if we don't cover them in course. And so we're going to try and give you a good foundation to read more. That's, again, the goal of the course. Quantum error correction, threshold theorems, super interesting if you like theory. Threshold theorems are like a whole thing to run through to try and prove one of them, or to try and improve the bounds, to try to see if the bounds work, to see how far the devices are from the bounds, to see what happens if you change one gate for another. Does the threshold go up? Does it go down? Actually trying to implement the threshold theorem, or not threshold theorem, but implement the idea of thresholds. So just to say now, the idea of the threshold is, where's the clock?
It was the batteries are dead.
Well, thanks.
Yeah.
Yeah, I mean, it's up here. Nice. Looking though. Any case, yeah, so quantum error correction is also a super important thing around quantum computing. And I even gave a template project. So if you guys have no idea what you want to do, there's an already finished abstract. If you don't have time to write an abstract this week, I mean, it's the first week of the term, please tell me you're not already like overwhelmed. That's not going to bode well for the rest of the term. But yeah, nonetheless, there's an abstract. So I gave some notes about how to write an abstract inside of it. All right, so course philosophy, there's two aspects of philosophy that I think are worth mentioning at the top level of this course. First aspect is teaching philosophy. For me, there's two aspects of teaching philosophy that I'm interested in. And one is helping students appreciate what's going on, aesthetic appreciation. I have no idea how to spell aesthetic. Second thing that this course is all about, and you will, if you haven't got the sense of what this course is designed to be, it's designed to be a roadmap, designed to be a way to see through the force, way to understand whatever new information comes in and how it fits into the rest of the information that's out there, way to see the whole literature. That's the idea. You can pick up a paper, glance at it, oh, this is using Grover search. Oh, this has a quadratic speedup. Oh, this has an exponential speedup. It must be connected to the quantum Fourier transform. How can you see things in a way that allow you to see through all the things that people have written? How do you know if you want to read a proof? How do you know if a proof is worth reading? How do you know if the paper is going to work on a real device? Right? You're going to think through these things over the course of this. So the second thing I like to do is guided inquiry. Okay, so these are my two pillars of my teaching philosophy. There's a whole page version of it, but this is the two main things that I try to impart when I'm teaching a course at my best. Okay, knock on wood, we're there. Right? So this is teaching philosophy. The second thing of philosophy that's probably important to talk about now is quantum philosophy. I'm going to talk about it now because I want to talk about it later. This is not a philosophy department. This is not a philosophy course. There are philosophers over there or somewhere on campus who do quantum information. They actually think about quantum effects. They think about what happens, wave function collapse, and interpretations of quantum mechanics. All these things I dislike. And I don't mean that I dislike their work, but I don't like that subject area. It's not something for me because I'm not in the philosophy department. For in the philosophy department, these would be fantastic arguments to hold. We're not in the philosophy department. We're not in the business of philosophizing. We're in the business of understanding what happened in the experiment, in the business of knowing what the predictions of the outcomes of some trial that we did, right? If we're going to shoot a laser at something, we should expect to know, or not expect, but to find out what happens when light matter interaction occurs. We're not trying to do this as a philosophical exercise. We want to know what happened. And so with that, my take on quantum philosophy was heavily influenced by my time in Vienna. I spent a few years there during a postdoc, and in Vienna, there was a very huge emphasis on quantum philosophy, about the foundations of quantum mechanics, about what does it mean, what are the axioms and things like that. And I've spent a lot of time thinking about it, maybe against my will, to speak at a seminar, and you're listening, you're not going to turn your ears off. So thinking, right? And what came out of this is this approach to quantum mechanics kinematically. It gets rid of a lot of things that have to do with philosophy. It doesn't say that the philosophy is not important or that it's not there. But what you will hopefully come to understand is that the philosophy of quantum mechanics is only there by virtue of the philosophy of probability. No one has a problem with saying it's a 1 in 52 chance of getting an ace heart, ace of hearts, right? So the point is that's not a hard concept. You can go to a kid and say, do you think it'll probably happen? And they'll say, yeah, I think it'll probably happen. So it's used it colloquially without any qualms or hesitations. So in quantum mechanics, the fact that it becomes this huge surprise that things can be measured is something we're going to try and alleviate by starting with the thing that is measured, probability functions. You measure probability functions, and no one has a problem with this, right? So we're not going to have a problem with this in quantum mechanics either, because we're going to start with probability. So if you have questions or foundations of quantum mechanics, what you really have questions are foundations of probability theory. There are a few things that intersect in interesting ways, but at the highest level, any intersection they have is almost certainly because of probabilities foundations, which are interesting philosophically and mathematically and a lot of other ways that I do not care about. I'm not a probabilist. And not to say I don't care about it at all. Of course, I'm interested in learning. So if you want to teach me something about it, feel free. But will I go out and hunt down that information, write a whole lecture series about probability theory? Probably not. So probability first. And this way, we're going to think of quantum mechanics as an extension of probability. This will hopefully allay whatever conceptual problems you have with measurement, whatever problems you thought you had with measurement, whatever you read about people who have problems with measurement, the Bohr-Einstein debates, all these things that are historical are not going to affect us at all. And in fact, the reason that we're going to take this route is that this will be much faster route to information theory. Information theory requires probability. So we're going to start with probability. That'll get us information theory. We could skip over quantum, go directly to information theory, and then come back and do quantum information theory. No, we're going to do probability, then we'll do quantum, and then we'll do quantum evolution, and then we'll do how this connects to information theory. Okay. All right, so then I still have 10 minutes.
Or 12 minutes.
I don't have too much more to say. What we're going to do for the rest of the lecture and perhaps on Wednesday is just discuss quantum technology a bit. This course is not a technology course. So if you want to discuss quantum technology a lot, sorry, you guys are sorely disappointed. This is a theoretical course, not a high theory course. It's a theoretical course that we're going to treat quantum devices like people treat cars. If you're a race car driver, you need to know how the car works. You need to know what it can handle. You need to know if you hear a certain sound, what's going on, but you don't need to fix everything. You don't need to know the exact, timing of the cam cycle and, what the injection rate is. Like, you don't need to know how much it's injecting at you don't need to know what the RPM maximum, you don't need to know any of that stuff. You need to know what the car sounds like, how it drives, and how it feels. So we're going to try and get you an overview of how the devices work, and then we're going to move past it. And that will be today and maybe a bit of tomorrow, but there's not much about devices here. And if you want a lot about devices, come to lab. Lab will be the great time for you to learn as much as you want about devices, because we'll be able to play with the actual devices that really are present inside of the world. Okay, so just to say a little bit about why everyone's interested in quantum, or not even why, skip the why. Everyone is interested in quantum information science. How do I know everyone's interested in quantum information science? That you look around the world at all the different places that have invested in quantum information science. Australia has a huge industry around thinking about quantum devices, silicon-based quantum devices. China, the United States have both invested heavily inside of quantum computing, inside superconducting qubits. Russia, India, Canada, European Union, Vienna. I was in Vienna Center for Quantum Science Technology, so I shouted them out explicitly. But yeah, so it's a worldwide effort that everyone's investing heavily in quantum computing, thinking about what it can be used for, what are the devices for, what are the upsides, what are the downsides, how much is it going to cost us, how much are we going to invest, who's going to have the first flagship experiment, who will have the second flagship experiment, who will have a bigger flagship experiment, and so on and so forth. And so there's a lot of investment going on. This is actually a great time. If you were to leave right now, walk outside and ask for a job in quantum information science, I would like you to be prepared for the interview, right? But there's a lot of interviews to go on. So if you're not prepared for the first one, go for the second one. If the second one doesn't go well, go for the third one. Like, there's just a lot going on now. So the main idea is that all over the world, wherever you want to go, pick a place and start applying, right, or whatever. I mean, the point is, this is a worldwide effort. For those of you who have not seen quantum information science before, or have seen not very much of it, I did write with my research group, hey, Brent, shout out, a review article about quantum computing that is largely an outline of the course. Okay, the course is a little different because 9 weeks, 3 by 3, the paper's not written in 3 by 3 format. But nonetheless, the ideas that are in that paper are going to be the guidance for how we go through our discussion. If you read this paper, you can probably read it over the weekend or read it over, a day or so, because there's no technical content to it. It's a lot of introductory aspects of it, point you in a lot of different directions, a lot of articles that are references that are hopefully at the height of references. Tried my best to find the best references. So if you want to know references, go look at the appendix for this paper. We'll have references about every single one of the devices that I discussed. We'll have references about quantum primacy. We'll have references about error correction, for instance. And so there's something that you are dying to get to now, and we're not going to get to it till the third unit. Then just read through this, have a look. If you're thinking project ideas or things that how's my project fit into the bigger picture, have a feel to look at this paper. Yeah. Okay, so then a little bit more about what we are here for. We're here to talk about quantum information science. Quantum information is based on the idea that quantum technologies. Quantum technologies are devices, detectors, communication systems that rely on uniquely quantum resources. Okay, so that's important to underline there, uniquely quantum resources. When people talk of quantum computers and then they talk of classical computers, I do not like the term classical computers. There's nothing classical about a device that's built at nanoscale, right? Just because you can't see it. I mean, it's already. I mean, there's nothing classical. You couldn't build this out of billiard balls. I mean, you could, but I mean, come on. Right? So the point is to fabricate these devices. You use quantum mechanics. Use light matter interaction. Use your understanding of atomic vapor deposition. Right? All these things that come into building microprocessors. So if the microprocessors themselves are conventional and quantum, what's the difference? The quantum devices are relying on uniquely quantum effects. What are uniquely quantum resources? That's what we have a whole course about, okay? So that's the first part of the course, quantum kinematics. So that's talking about what is the unique resource. And then we go into quantum computing for the second unit, which is using these technologies to speed up or otherwise improve time to solving the computational problem. So we want to know about, can I solve some 3-sat problem? Can I solve some optimization problem? Then this is where quantum computing comes in. And as I said already, we're going to view quantum theory as an extension of probability. Okay, and now for your.
So right now, there isn't anything to say that quantum technologies will or quantum algorithms will always be superior to classical.
Oh, there's things to say this, but you have to be very careful because you have to read what they said, right? We'll get into it, but in Grover's search, you get Grover's search itself is a nice paper, the paper that Lo Grover wrote. But at the same time that he wrote that paper, there was also a paper by Bennett Bernstein, by BVVV. So this paper, this B Bernstein, Bennett, Brasser, in Vazirani. In any case, this paper comes out the same year as the Grover search paper, and it shows that you cannot get anything but a quadratic speed up on an unstructured optimization problem. So it's fantastic that the proof that Grover search is optimal shows up at the same time Grover shows the algorithm, right? So you can't do better than Grover search for unstructured problems. And this is one answer to your question. Right? There's other answers to your question about what are some structured problems that allow for quantum speedups? What are the structures that allow for simulation of quantum systems is the other way you can think about that problem. So we've got a foundations of quantum information processing. We'll talk about low entangled states. Low entangled states can be simulated efficiently. So that means that if you have high entanglement, at least you know you can't use that trick to simulate. However, you can get high entanglement with certain classes of simulable gates. Those gates that are simulable still maintain some symmetry, which allow you to get away with simulating classically. And so once you start getting rid of symmetries, getting rid of completely unstructured problems, somewhere in the middle, something like quantum Fourier transform or integer factoring have structures that allow you to get out exponential speedups. But to say that every quantum algorithm is going to be better than every classical algorithm is not true. And say it's also there's some important asterisks around that point. So even with something like Grover search, if you guys remember what Grover's original setup for the problem is, he wants to search a database. Searching a database means you need to be able to access the entire database in superposition. That means you need to be able to upload and save and store a bunch of data in superposition, which means you need to have working quantum memory. And you need to have a large working quantum memory. Otherwise, there's no point in searching over a small database. You could just do it by hand. Further, if you were to go talk to an actual computer scientist over in our CS department about Grover search and think about what happens in an unstructured search situation, unstructured search is terrible and it's really hard. You have to go through everything. At the worst case, you have to just look one by one by one. And this can be really bad if there's an exponential number of things. However, if you have a database, you need to search through this unstructured. The most sensible thing usually is to structure that database. Then you don't have the Grover search problem anymore, right? So you can think about it this way, is that Grover search works as completely unstructured, but usually people structure things. Usually problems have structure. And so even integer factoring is a very interesting problem because it shows up in a very, very, very narrow, tiny point inside of complexity space. We talk of how computational algorithms are divided. This is a very strange problem that's NP, but not NP complete. We'll get into more details about what that means, but that's to say that factoring is a very unique problem that really allows for quantum speedups. To add one more asterisk to that, factoring is not known or not provably known to be hard for classical computers. So actually, there's no proof to say that you can't solve factoring. Right? And if you're really intelligent, you really want a cool 9-week project, get an efficient factoring algorithm, right? You know what I mean? Grit your teeth, man. What's up? So,
Nobel Prize.
I don't know if you get a Nobel Prize for doing that. I mean,
They'll probably lock you up somewhere for the NSA.
I mean, you could get a lot of money and just start reading all the emails, everybody. And you don't need to do anything. Okay. All right, so then just to close out this lecture, I have, it's 55, right?
I was the same.
Right,
about
so I have-
the time. You've got a lot of time.
Yeah, I got 55, right? So this is great. A lot of time to talk about a little bit of things, which is great because I don't want to say too much about this. I'd rather not say anything wrong than just not say anything, but I can't not say anything. I had to say something about technology. Just would be completely remiss to teach a class of quantum information science with all the things that are going on in the literature to not say something about technology. So we're going to take a moment to say a few things about technology and then we will stop. There are 6 technologies that I've highlighted in our notes. These are not the only 6 technologies. In fact, there are other technologies. Yes, you guys all have a copy. Great. I will post all the notes. So I'm actually planning to post them all on GitHub, so you can just pull them all. We'll post the notebooks and everything there. So the 6 technologies that we're going to talk about are just the ones that are listed here. So quantum optics. Quantum optics is a very important aspect of doing quantum computing because you have flying qubits in some sense. So the photon itself has a path that it goes along. So if you have some beam splitters, just controlling which path it goes on the left path, it goes on the right path. That's one way of thinking about information, left or right. That's a 0 and a 1. You can think about the spin of a photon, be circularly polarized, a left, circularly polarized to the right, vertically polarized, horizontally polarized. So we have entire degree of freedom, 2-level degree of freedom in the photon just because it has 2 states of polarization. So you get modes, and you also get the ability to have them entangled, which entangled photons through a process called down conversion. Down conversion is basically taking a photon and pumping a crystal, and the crystal comes out, it pumps out 2 photons. Those 2 photons come out in a way that you don't know which one's which, then you can think that they are correlated in some way, shape, or form, and that correlation can be used as entanglement. The company PsiQuantum and Xanadu, these are 2 companies that built out their quantum optics setup. The idea of what they're doing at the highest level is that they're multiplexing this down conversion. Down conversion for 2 photons, you pump it, you get out 2 photons. You want down conversion for 4 photons, you have to wait a lot longer for it to pump the crystal until it gives you back 4 photons. If you want 8 photons, you want 16 photons, so on and so forth, you have to pump the crystal and wait. And so what they've done is done as a percolation problem. You guys know a percolation problem? Mind. Moving on. It's done as a percolation problem. Percolation is actually a very interesting thing. If you are interested in finding out more about statistical mechanics and how errors may or may not ruin something, percolation theory is a fantastic thing to look into. So if you're looking for ideas for projects or something maybe connected to your thesis, whatever. Nitrogen vacancies in diamond. This is listed here, but nitrogen vacancies in diamond, along with nuclear magnetic resonance, do not form the basis for quantum computing devices at scale. Variety of reasons. In the case of nitrogen vacancies, you have, so if you can see here, it's this is a diamond lattice, a bunch of carbons everywhere. There's a nitrogen here, and then that means that there's a pair of electrons or a vacancy left behind because nitrogen's missing one of the 3 bonds that it makes. And so this electron, the electrons inside the hole, be manipulated. This gives you a 2-level system. The hard part about scaling up nitrogen vacancies is that you have trouble implanting these nitrogens at a uniform distance. Also, you need isotopic purity, so you actually can't use the diamond off of your wife's finger or whatever. Because that diamond would have C13 as well as C12. C13 has a nuclear spin, which causes decoherence. And so if you make a random crystal with carbon, it's going to have C13 randomly placed, and I have the nitrogen vacancies implanted at some random location. And this is a difficult engineering challenge. However, these diamond vacancies are developed quite highly as far as technology goes for sensing very, very small magnetic fields. It's actually fantastic what you can do as far as magnetometry goes with nitrogen vacancies. Neutral atoms, this is in contrast to ionized atoms. So neutral atoms, this is actually a picture of really large s orbital, or I don't know if it's s orbital, one of the very large orbitals from the hydrogen solution. And this is plotted here. And what you're seeing is that this is just a high N number for one of the hydrogen solutions. If you know the hydrogen solution, it's great. If you don't, sorry guys. These are called Rydberg excitations, because the Rydberg series is from the hydrogen atom, where you look at what happens for just the electron going around the proton. These show up when you start talking about highly excited states of an atom, because you take one electron and you move it very far away from the atom. The analogy I'd like to give for this is thinking about Halley's Comet, which goes very far away from Earth, comes back, interacts, and then goes very far away, comes back to Earth, interacts. So this is the same idea of this orbital being very far away, but it's because this electron's so far away from the nucleus, all it sees is the missing charge that it left behind. So it sees it as if it were a proton. You can actually solve this with the same solution that you use for the hydrogen. There's basically a plus charge left behind, electron's very far away, a minus charge, and these two are orbiting one another. So the Rydberg analysis works here quite well. What's also amazing as a side fact, yes, I still got 5 minutes. So the side fact about hydrogen solutions, the hydrogen's principal, so with the principal quantum number, as n goes up, the size of the hydrogen gets larger and larger and larger. These orbitals actually get really, really large. And in fact, it actually becomes a problem if you actually try to compute the partition function of the hydrogen atom. It actually doesn't converge because these very large n values just don't. I mean, the series just doesn't converge. And you have to be careful about how to make it converge. Okay, so Rydberg excitations. Rydberg excitations, we have one state that's Rydberg excited, the other state gets Rydberg excited. Because these electrons are so far away from one another, they start interacting. And this is what we call Rydberg blockade, because if one's excited, it's going to change the energy of exciting the other. And so you have one excitation, and then it will prevent the other one from being excited. And that's like doing some interaction between the two atoms. And so that's how you can mediate interactions. Each atom's held inside of its own little trap by optical tweezers. You send a laser to control the state of that particular atom. And then you excite it to this large Rydberg state to have them interact with one another. Neutral atoms, there are neutral atom devices that are coming available soon. So keep an eye out for that. Nuclear magnetic resonance is a cool idea. In fact, a very cool idea. If you ever hit your head, you have to go to the hospital, that cool idea will be used to image your brain. The idea of nuclear magnetic resonance, magnetic resonance imaging, the difference between these two sets of words is nuclear. And the reason that the medical term does not include the word nuclear is that after World War II, no one wanted to get their head scanned by a nuclear magnetic resonance. But it's actually the same technique. You have some radio wave frequency that's going to be on resonance with the microwave, with the transition that's split between two hyperfine levels or two fine levels that are inside a magnetic field. And that's the main idea. This main idea of nuclear magnetic resonance is super important because it also gives us a way to understand a single qubit. A lot of the language of qubits is coming from the NMR family of technologies. Superconducting loops, I won't say much about this. I will say that Josephson junctions are cool, and I won't say much about it because there's a lot more information about it available widely from a technological point of view. This is a dominant form of quantum computing devices that's available and will be available for the foreseeable future. Trapped ions, similar idea to neutral atoms, except instead of trapping them neutrally, you ionize them. Okay, great. Now they're ionized. That means they respond to electric and magnetic fields, and you can trap them inside of a trap. You trap different atoms. You use the hyperfine states or their fine states as qubits. You can have them interact. The interaction inside of ions is actually really interesting because inside the small trap there'll be 10 or 15 ions. Those 10 or 15 ions form a crystal, and that crystal, the vibrational modes of that crystal are actually what allows coupling between the different atoms. All right, last few words here are that there are a lot of companies that have realized these things. Here you can see how many different companies have superconducting loop, right? D-Wave, Rigetti, Google, Amazon, Alibaba, all these different companies have all invested in superconducting technology. Quantinium and IonQ are focused on trapped ions, neutral atoms. Here's a couple of companies that are looking at those. PsiQuantum and Xanadu, as I mentioned, are doing quantum optics. And then just to close everything out, what we will be using for our course in order to get a nice view of how these devices work, right? The same way that I said, we're gonna look at it at the level of a car driver. We're not gonna be down in the details of getting our hands dirty with this stuff. We wanna know how it runs. And so we're gonna use Amazon Braket, which gives us a very clean, steering wheel to using the device. And it's not a clean steering wheel if you don't want it to be. You can get in there and go into the hood and see what's going on, test out the decoherence times, everything else. There's quantum annealers through D-Wave, trap-based ion computers through IonQ, Rigetti, and Oxford Quantum Computing are available for using for superconducting qubits. So the idea is that we're going to have our lab tomorrow. We're going to help you get started with Braket as far as getting Amazon Braket installed on your local device. In the near future, we will get you credits for actually running on the real devices. And in the following week, we'll start with Lab 1, which is around the single bit and the single qubit, which I think is a fantastic lab. I mean, I hope, right? You guys give me some feedback, okay? Whole thing, this entire course, you guys are welcome to give me as much feedback as you please. I want this course to be good. If you see anything wrong, tell me, I'll correct it, and we'll do our best, okay? That goes for you, that goes for me. Good? All right, that's our technology lecture.
So Amazon Braket also though has like classically simulating like quantum circuits. Is,
Yeah,
like,
we're gonna do
another
that too.
aspect.
We're gonna use the managed simulators for the second lab.
Okay. Cool.
First lab, if you get to it, you can use your credits on the actual qubits, or you can wait till the second lab.
Use them all in the first.
Third lab, yeah, don't use them all in the first run, right?
I think we can also just run some of those quickly, right? Like,
You install it, yeah.
I started a Slack channel. I'll be adding